Okay, so this problem is, we actually did this problem, well, I want to say it the right way. Hold on here. We actually did this problem in our last class, last Thursday's class, where we did find parametric equations for the tangent line to the curve with these parametric equations at the point root 3, 1, and 2. Okay, but now what I want to do is I want to illustrate this by graphing both the curve and the tangent line on a common screen. And the reason I think this is helpful is because I'm thinking about your, next exam, which will cover section 10.2, and I'm thinking it would be nice in a way when you get your answer, before maybe you type it in and hit submit, it might be nice to check the answer. And if you can graphically check that your tangent line is tangent to the curve at a particular point, I think that's very valuable. So that's why I'm doing this problem with you. So, all right, on that note, let me give you a moment to copy that down. Okay, so what we want to do is we want to go to the program in MATLAB to help us with this illustration. So on that note, what I'd like you to do, hold on here. Yeah, what I'd like you to do is go into your Blackboard, okay, and look under MATLAB programs. So I'm going to do that as well. Hold on here. Share application. Okay, is everybody seeing the Blackboard screen okay? Good, thank you, John. Thank you, Ryan. All right, so you just go to MATLAB Programs, thank you, and you go to MATLAB Programs. Click here to see MATLAB Programs, that'll be helpful. And I got a couple of new ones. So we're talking about section 10.2, okay, and this MATLAB program will help you draw the tangent line on a space, to a space curve. Okay, so just click on the MATLAB program, and it should download to your computer a MATLAB program that's going to do this. And the MATLAB program is tailored to this example. So click on the MATLAB program, and if you have MATLAB installed, which you should have, everybody should have MATLAB installed by now, it should bring up MATLAB. Okay, and I'm going to go find my MATLAB program here. Okay, and who is seeing this on their own computers, this program? It's an extraneous one here. Let me get that off. Okay, good, Christopher. Good, John. Good, good. So what I'm using here is called the fplot3 command. Okay. So what I do is, there are different ways to graph space curves. Like we saw, for instance, easy plot 3. That was a command that was used to graph a space curve. But what I'm doing now is I'm using a command called fplot3. All right, and what I do is I type in, you can see here I have the parametric equations, okay, for my space curve. Okay, and I'm going to graph the space curve from 0 to 2 pi. And I picked that because that should do one, the curve is, because the curve, the x, y, and z components of the curve consist of cyclical cosine and sine functions. Well, the period of a cosine function is 0 to 2 pi. Well, and of course the cosine of 2 times t, that would have a period of pi. So what I'm saying is from 0 to 2 pi, that's going to give me enough, that's enough domain on t to be able to graph a complete loop of this curve. And then I use the command called hold on, because what I want to do is, after it graphs the space curve, that space curve, I want the MATLAB to hold on because I want to add another plot. And this second plot here, whoops, hold on, you got to be careful. Hold on. Yeah, this second plot here is the plot for the tangent line, and we found those x, y, and z those parametric equations for that tangent line. We found in last Thursday's class. Okay, and you'll notice that the domain I'm going to use for t is from negative pi over 3 to 2 pi over 3. Why do you think I would use that? Why don't I use 0 to 2 pi? Why not just use 0 to 2 pi? And I guess I can tell you, if you just use 0 to 2 pi, you're not going to get a very good picture. What value of t is, if you look in your notes, what value of t corresponds to the point square root of 3, 1, and 2? Right? We're trying to graph the tangent line to the curve at the point square root of 3, 1, and 2. So what value of time does that correspond to? You remember from your notes? If you look in your notes for last Thursday's class, that's right, Robin, t equals pi over 6. So what I wanted to do, t equals pi over 6 is 30 degrees. So what I did was, let me have an interval that goes from negative 60 degrees to 120 degrees, or negative pi over 3 to 2 pi over 3. And that's centered about t equals pi over 6. And hopefully it'll give me a decent graph. I mean, it took me some time to figure this out. I just didn't, do this. But I experimented just like a student would. And, it's something you're able to do too. Okay, and then I want to label my x, y, and z axes. So I'm going to just copy all of this. I'm going to copy all of this. I'm going to go to the command line and say paste, and then I'm going to hit enter, and it should produce a graph. Okay, now it got me here somewhere. Hold on. Um, hold on. Let me fix that. See? All right, let me try it again. The original code, see, whenever you edit things, you can make unintentional errors. The original code had a square root of 3 on it. So let's try it again. Okay, let me just do it one more time here. Okay, good, good. So when I do this, when I run the code, I got this. How many are getting a picture like this? Good. And does this, okay, good, Ryan, good, Ryan. Um, does this seem to confirm, is this a geometrical confirmation that the parametric equations for our tangent line are correct? Does this look like a tangent line to the space curve at a point? It does. So, you know, I think it's a very nice thing to be able to verify your answer geometrically. You know, I just think that's a nice skill. And of course, we know the way the axes are. It's not like the axes, you know, the x and the y axis are, and the z axis are like the same axes, but of course, we can rotate this and hopefully get things like we're used to, you know, like the. But you can experiment with that. I got lucky the last time when I did this. Hold on. I don't want to spend too much time on it, but I'm just saying, you know, you can play around and rotate the axes. Hey, there we go. There we go. There we go. How about that? There we go. There we go. So, you know, you can play and rotate the axes. But, well, no, that's not right because the x-axis is normally where the y-axis is. So you just got to rotate it and play around with it. But are there any questions on that? How many think this is pretty cool? Okay, thank you, Robin. Thank you, Ryan. Thank you, John. It's like, you know, I like Iron Man. You know, when he had his new suit and he had new powers. That's how I think of this. You know. Thank you, Naima. Thank you, Christopher. I don't know if that's a good analogy, but anyway, all right. Let's continue on. I want to do some more problems from section 10.2. And incidentally, just for the our recording, there's the code that I used, so it's in the recording. Okay, there's the graph. Great. Okay, let's look at another problem. Okay, let me give you a moment to copy this problem down. Okay, so in this problem, we're given two space curves. Okay, we're given two space curves, here and here. And we want to know at what point do the curves intersect, and then find the angle of intersection correct to the nearest degree. So can you think of an application where this might be good to know how to do? That's right, Christopher. Projectiles or planes. Sure, absolutely. Absolutely. We want to know at what point two planes would, collide. We don't want that to happen, but it's of importance. And certainly if a missile shot and we need to intercept a missile, we'd like to know at what point our missile would intercept their missile. Like I said, over the ocean, for instance. There are a lot of, you imagine, all the good applications here. We don't want to shoot missiles, but we don't want to get hit by a missile either, right? So, all right. So, well, at the point of intersection, okay, the coordinates for both of these space curves have to be the same. That's important. So that means that t would have to equal 3 minus s. 1 minus t would have to equal s minus 2. And 3 plus t squared would have to equal s squared. And if these two curves do intersect, that means there has to be a value for s and a value of t such that this set of three equations holds. Okay. So on that note, let's look at the solution. So where the space curves intersect, where the space curves intersect, we must find values of t and s so that these three equations hold. And that means the components of the one space curve equal the components of the second space curve. I want to say that more clearly. The components, the x, y, and z components of the one space curve have to equal the corresponding x, y, and z components for the second space curve. Okay. Okay, so here we go then. We're going to work with the first and second equations. So what I'm doing here is t equals 3 minus s. Okay, I'm taking the 3 minus s and I'm substituting it in for the t that's there in the second equation. Okay, for that t. And so we get 1 minus the quantity 3 minus s equals s minus 2. And we end up getting s minus 2 equals s minus 2. And so this is what's called non-informative. Try to spell that. Okay, that's, try to get this mouse to, that's what we call non-informative. We got no information. So, okay, we move on. Let's work with the first and third equations. So again, what I'm going to do is I'm going to take t equals 3 minus s. I'm going to substitute that in for the t here in the third equation. And that's going to get me 3 plus the quantity 3 minus s squared, or quantity 3 minus s squared equals s squared. And I'm going to solve that, and I'm going to get s equals 2. So I'm going to get a value of s that works. And if s equals 2, then that means by the first equation, t equals 1. And so the point of intersection is going to be 1, 0, 4. These two space curves do intersect. And how do I get 1, 0, 4? Well, just take take t equals 1 and s equals 2 and plug it in either of the space curves into the components. Okay, and you'll get 1, 0, 4. So like if you use this first space curve, you got t 1 minus t. I'm talking r. Well, yeah, I mean r1 of 1. That's what I'm computing here. T, you get 1, 1 minus 1, and then you get 3 plus 1 squared, which is 4. And similarly, if you take s equals 2 and you plug it in the second space curve, you also get 1, 0, 4. Hold on here. Right. All right. Very good. Now there was a chat that was sent to me, but I don't know if it was I'm gonna just leave my chat thing alone. I can check if you sent me a private chat, send it to me, resend it later, because what happens is I don't want to lose the main chat room right now. And sometimes, but I mean, if are there any questions so far? Okay, all right, so that's great. We know where the points intersect. And now we want to find the angle of the intersection to the nearest degree. So what we can do, may I move to the next page? Are we comfortable so far? Okay, Christopher's good. Brian's good. Okay, so, okay, I have a little picture here to help me. How are we going to find this angle of intersection between the two curves? At the point, find the angle of intersection between the two curves at this point to the nearest degree. Well, what I've done here is I've drawn just a little picture. Okay, pretend this is R1. You got the one space curve, R1, and you have another space curve, R2. And actually, let's just say they're going that way, all right? And here's the point of intersection. 1, 0, 4 is right there. And we're looking for the acute angle between the two space curves. Okay, so this is the angle we want right here. That's going to be your theta. Well, where did you learn about like what formula had a theta in it that you learned so far from like chapter 9? What concept had a formula that had a theta in it? The dot product. That's right, Christopher. And the dot product involved vectors. So what would be wrong with finding the tangent vector for the first space curve at t equals 1, and then finding the tangent vector for the second space curve for s equals 2? Okay, because those tangent vectors would be tangent to the space curves at the point 104, because at the point 104, at that point, that's when t equals 1 and s equals 2. So we find the derivative vectors for R1 and R2. Okay, those derivatives vectors for those space curves, and then we evaluate the derivative vector for the first space curve at t equals 1, and we evaluate the derivative vector for the second space curve at s equals 2. And now what we're trying to do is we need to find the angle between those two vectors. So it boils down then to a dot product problem. Are there any questions with what we're doing here? Are there any questions? Please let me know if you're uncomfortable. All right, well, then, of course, the dot product between the derivative vectors is equal to the magnitude of the first derivative vector. This should be, I left out a little something here. This should be, hold on here. Left a little something out here, but I'll fix it right now. This would be r prime at 1, right? Okay, times r prime, well, it's the derivative of r1 evaluated at 1, t equals 1. So we're going to find the magnitude of that. I'm sorry, I want to get this looking good here. Can't help it. Can't help it, class. Being neat has helped me out of so many problems in math, you know. Denoting things properly. I don't even like that. I'm going to do this right. I'm going to do this right. There we go. Okay, so this step now should be clear, and then the cosine of theta will equal 6 over the square root of 8. So theta is 54.7 degrees. And, of course, in WebAssign, this kind of problem, you always have to read those instructions carefully. If they want it within the 10th place or 100th place, you just got to read the instructions carefully. But there you go. So how many think that's a pretty cool problem? Yeah, Ryan likes it. Robin likes it. Yeah, I mean, this sounds like an engineering problem to me, and it is. And many of you are engineering majors, right? So, okay, I'm going to do another example from section 10.2. Are there any questions on this problem? May I move forward to the next example? Okay, Ryan's good, Nama's good, John's good. All right, very good, very good. Well, let's move forward then. Okay. I'm going to let you copy this example down. Okay, so this is a truly fascinating result. Truly fascinating result here. It turns out that if you have a space curve and the length of your space curve, regardless of what value of t is, if the length or magnitude of your space curve is always a constant, turns out then that the derivative of your space curve, r prime of t, is going to be orthogonal to the space curve itself for any value of t. Orthogonal, of course, means perpendicular. Okay, this is now for any value of t. It's not for some value of t, it's for all values of t. So the derivative of the space curve, the derivative vector of the space curve, will always be orthogonal to the space curve itself, so long as the length of your space curve is constant. Okay, and this result is going to be very, very important for a problem for section 10.3 in particular. It's going to be very important. Let's go ahead and look at the proof of this. So first of all, what I do here, the actual solution is on the left. But what I wanted to do was I wanted to just give you an example. You might be wondering, well, what kind of space curve would always have the space curve always have constant length? And an example is a space curve like this. Okay, so if you're, I'm doing something simple in two-dimensional. It's two-dimensional space. Okay, but you know, a helix would also apply here. But let's just stick with this. So let's stick with something you've seen. You've seen parametric equations for a circle. You let x of t equal cosine of t. You let y of t equal sine of t. Okay, you've seen that. And if we were to take the length of our space curve vector, we know we square each of the components, add them together. Well, what's the square root of cosine squared plus sine squared? Why is cosine squared plus sine squared of our angle t equal to 1? Where do we get that from? That sounds like an identity. Does anybody know that identity? It is an identity. Okay, it has a special name. Cosine squared of an angle plus sine squared of an angle always equals 1. That's called the Pythagorean identity. Okay, at least I want to be careful. I think it's been referred to that, but look, you know that's true. Okay, so look, yeah, okay, thank you, Christopher. Christopher confirms that. All right, great. So what I've done here is, hold on, I don't know, hold on, let me try this. Hold on, hold on. Maybe I got to erase this. Hold on. What I'm doing is I draw the space curve, and I'm going to try. Boy, wouldn't this be nice if I could make this work? That's pretty good. We'll go with that. So there's the space curve. This is, hold on here. Whenever you draw a space curve, you want to indicate the direction the object on the space curve is moving. And this object's moving counterclockwise. So that's space curve C. And here is parametric equations for the space curve. And there actually is the space curve. I mean, there is the position vector. Hold on here, I got to get this right. Here's the position vector for the space curve, right? It's a little tricky. And on the other hand, here is the derivative vector for the space curve. Maybe I'll try putting it in green. Okay, and so as the blue position vector changes with respect to time, for each value of time, the tip of that position vector gives a, there's a point for every value of t that the tip of that, for the tip of that space, for the blue position vector, r of t, for every value of t, the tip of that position vector dictates a point. And if you put all the points together, you'll trace out that red space curve C. Well, the derivative of the space curve is r prime of t, and that is, if you take the dot product of r prime of t with r of t, you're always going to get 0. So for any value of t, those two vectors are orthogonal. And that's an example of a space curve whose length, of a space curve whose the length of its position vector is constant. Now we go to the proof. So on the left side, let's assume that the length of your position vector is constant. Okay. Well, you can square both sides of the equation. So you get the length squared is equal to c squared. But the length squared of a vector is equal to the dot product of the vector with itself. Okay, how many learned that from like their homework? Or how many realize that? Hopefully you realize that. It just like okay, well, like if you let's say you have the vector 1. Let's just take an analogy, an example, 1, 2. Okay, the magnitude of 1, 2 of that vector is square root of 5. Okay, so this is an aside here. I'm trying to show you why the left side here of this equation. I'm trying to show you why the magnitude or the length of a vector squared is the same as the dot product of the vector with itself. So as an example, I have the vector 1, 2. Well, the length of 1, 2 is the square root of 5. Okay, well, if you dot product the vector 1, 2 with itself, okay, what are you going to get? You're going to get 1 squared plus 2 squared, and that indeed equals 5. So if you take the magnitude square root of 5, or the length of that vector, and square it, you get 5. All right, that's right, Christopher, that's right. Okay, how many was this little example here helpful to help you feel comfortable going from here to here? Was this helpful, this little example at the top? Okay, thank you, Ryan. Thank you, Robin. Wonderful, wonderful. Thank you, Naima. All right, well, we proceed on here. We proceed on then. And what we're going to do is we're going to take the derivative of the dot product with respect to t. Of course, if we take the derivative of the left side of the equation, we have to take the derivative of the right side of the equation. So remember, the dot product, if you take the dot product of two vectors with respect to t, I mean, this is just going to be some function of t, right? That's just going to be some function of t. So All right, but how do you take the derivative of a dot product? Well, there is a rule. There is a rule in section 10.2, and you can look at the proof. The derivative of a dot product it works just like the product rule for a derivative of a product of two functions, only you have the derivative of a dot product of two vectors. And the derivative of a dot product of the vector r with itself would be the derivative of the vector r dotted with r plus r dotted with the derivative of the vector r. So these here are dot products. I'm drawing these dots very solidly. And it is a rule. It is a rule. You can look at it in your book. It is a rule. Okay. So maybe what I can do, if we have time, is I can show you the rule. But what happens then is the derivative of r dotted with r is the same as r dotted with the derivative of r. I mean, that seems to make natural sense based on the way the dot product's defined. And therefore, since they're equal, on the left side then, we have 2 times the dot product of the derivative of r with r. But then I can divide through both sides of the equation by 2, and I get that the dot product of the derivative of r with itself is equal to 0 for all t. For all t. Therefore, the derivative of r with respect to t is orthogonal to the vector for all t. And we've just proven the result. Okay, one moment. Let you copy that down. Make sure you're good with that. Okay, I'm going to get the ebook. One moment. Okay, so I'm going into the ebook, and you can go in as well here. I'm going to section 10.2. Differentiation rules. Okay, one moment here now. Okay, good. Finally got there. Okay, let me go to the ebook now. Okay, so these are rules. Six rules that are true. They're differentiation rules for, you know, you got the derivative for the sum of vectors. But look at like the first rule, but look at rule 4. Rule 4 says that the derivative of a dot product is equal to the rule on the right. And that's the rule that we used in that proof that we just did. So, and it's of note, look at rule 5. They have a rule for the derivative of a cross product. You'll have a problem in the homework that's an application of that rule. It's worth knowing. But let's prove that fourth rule. Let's look at the proof for the fourth rule. They go down here, formula 4. So what they do is they say, okay, let's let U and V vectors be defined with those component functions. Well, if you were to take the dot product of U with V, you would get the summation where I equals 1 to 3, each element being the ith function of F times the ith function of G. Okay. So, wait, hold on, wait, man, did I lose the book here? I don't know why I'm losing the book from time to time here. Hold on, let me bring it back. Okay, so we're looking at the proof of formula 4. Okay, so differentiating the dot product now, if we look at this part here, differentiating, let me just see here, is that, all right. Differentiating the dot product is the same as taking the derivative of that summation of those product functions. Okay, but the derivative of the sum is the sum of the derivatives. And then the derivative of f of I times g of I is just f prime g, f prime times g plus f times g prime. And then the sum of that sum of two functions is the sum of the summations, and then we get the final result. So now hopefully you appreciate the rule. How many think that's a pretty cool rule? So the point is now, the point is that in the theorem, or in the what we just looked at, we have justification now going from this step on the left to this step. It's justified by that fourth rule, fourth formula in section 10.2 for the derivative of vectors formulas. Okay, are there any questions on that? All right, who's feeling reasonably good? Okay, great, great. All right, good. I want to look a little. Let me stop the recording then for this section.